Okay,
thank you guys so much for coming today. Leo Jimenez will be presenting about the wearable exoskeleton design for stroke survivors.
All right. So my name is Leonardo Jimenez, and throughout my mentorship experience, I had the opportunity to work at UNC Chapel Hill's neuromechanics lab. I got to work alongside my mentor, Dr. Xiaogan Hu, and two grad students, Luis Vargas and Henry Shen. So before we go into the presentation, let's talk about technology in general. So many of you are probably familiar with Terminator, and even more recently, there are shows like Black Mirror. And because of it, technology tends to get a bad rep, right? Because of all the bad possibilities that there are. Well, at our lab, we have a completely different perspective. We know that in designing a new exoskeleton arm device, we have the potential to help millions of people improve their lifestyles, especially since many of them are suffering with the effects of stroke. Now, we may not have as big as an impact as our friend Wally, but we know the potential of this technology, and we find it very important to invest in it, right? So let's talk about what a stroke is. So there are two general kinds of strokes, and both of them just refer to any type of blood flow restriction to the brain. One of the first ones is known as a hemorrhagic stroke, and what that is essentially any type of internal bleeding in the brain, whereas an ischemic stroke is basically when there's a blood clot in the brain. And there's also something known as a transient ischemic attack, which is basically the same thing, but the clot goes away after a certain amount of time, right? But one of the biggest things about all of these forms of a stroke is that they all have the potential to do lots of damage. Some of these, the effects of a stroke can be hemiparesis, which is the paralysis of half of a person's body, or spasticity, which is a condition in which a patient's muscles are continuously contracted, and that can make day-to-day activities really hard. According to the U.S. Department of Health and Human Services, around 6 million Americans have to deal with the effects of a stroke on a day-to-day basis. So again, it's important to address. So one of the proposed solutions to this problem are upper arm rehabilitation devices. Of course, there are devices for legs, etc., but our study is going to focus on these devices. A previous study conducted by Masia Jaz et al. Looked at a variety of devices and proposed some critiques of them. Many of those critiques are the fact that some of these devices are incredibly bulky, so that means that they need support structures, and that in turn makes them not very portable. And this is an issue because not all patients can go to like a therapy session, and so the general idea is the more rehab you can get, the better and the faster you'll be able to rehabilitate. Another one of the critiques is that a lot of these devices don't necessarily have like torque force sensors integrated into them, so there's user feedback, there's a lack of it basically. And so sometimes these devices can either provide too much torque, too little torque, and it's not necessarily meeting the needs of the patient. And then there's also the difference between haptic passive and haptic active devices. Active just usually refers to devices that actually assist in flexing, extending, whereas haptic passive devices are a little bit different in the fact that they're not actually helping, they're just built with brakes so that patients don't overextend themselves. They're just there to prevent too much stress on a patient's arm. And like all of these issues tie into the safety and ergonomics of the device. Essentially, you want to make this experience one that's super comfortable for the patient so that while they're rehabilitating, they're not put in a position of stress. Okay? So this previous study helped us develop our research question, our first one being, how can we improve the current exoskeleton designs that are out there? Now, a lot of exoskeletons have like finger motions, elbow motions, and so what we wanted to do is limit our focus to the elbow joint, right? Because it's a simple motion, just flexion and extension, and that would allow us a lot of time to focus on creating multiple models instead of just trying to focus on one, so that we could determine like which is the best design. This led us into our next question, which was, how can the torque be transferred from the motors in the device to the actual elbow of the patient? This would require a study of the normal torque force that is provided by healthy individuals, which would then allow us to figure out, okay, how much extra force does our device need to provide to make up for the spasticity of the patient and the weight of the device itself. So in our methods to begin constructing our device, first what we did is we established the criteria that we wanted for our elbow exoskeleton. First of all, it had to be haptic active, but we wanted to build in a sort of passive element, which would come in through the back drivable switch. Basically what that would be is if a patient needs assistance flexing, but they don't really need it extending, the switch would turn off the device and then it would just utilize brakes to prevent the patient from overextending themselves. And then the device also had to properly transfer torque, which again leads us to that study that we're going to talk about in a second. And it had to be ergonomic. We wanted to be adjustable for different arm sizes, lightweight so that it wouldn't put too much stress on the patient, and we wanted it to be portable so that they could use it in their own homes. Another thing that we wanted to look into was the affordability of the device. We weren't able to get to this point because we weren't actually building it with metals, but at some point that's something we would like to do. So after we set this preliminary criteria, what we did is we started making our first designs. We used a study by Zia et al., which basically already put the motors at a patient's elbow, and we wanted to mimic that. And then later on, we'll talk about an issue that we found with this. But after that, we also wanted to go beyond just a simple strap that would go on a patient's arm, so we created a new fastening system based on the BOA snap system, which is just basically used on biking shoes, and we'll show you that in a second. So these were our first two models. This first one, the only real difference between them is that the first model, number 2 is basically only adjustable 2 and 1 in the vertical axis, whereas in the second model it's adjustable both vertical and horizontally for different arm sizes. And then that's what the BOA snap system looks like. Basically we just insert it into these little gaps, which is the circles on that first image. And then basically what you would do is you would twist it and it would tighten the top barrier so that it would sit on the arm and constrict it. And then in the second model, we would just use springs on those little T's on the bottom to constrict it horizontally. So what I mentioned earlier is that we wanted to investigate the normal torque forces that are provided by healthy individuals. Another study already looked into this, and basically what we wanted to do was confirm their data. What they originally did is they looked at the torque force that is provided by the elbow joint at different shoulder angles. So a shoulder angle at 0, 60, and then 135. And as you can see, the blue is the shoulder at 0. And what they found is that the max torque is elicited when the shoulder is to the side because the joint has to lift the weight of the arm against gravity, basically. And so ultimately our goal was verify it with a MATLAB simulation. So what we did is we created a simulation. We took the average length and the average size of an arm, and we made it run a trial of continuous flexion and extension over a 50-second period. After that, we looked at the angles at which it was moving, the acceleration and the velocities, and then MATLAB basically calculated the actual torque that was created for us. So as you can see here, we have H, V1, and V2. H is flexing here, V1 is out and up, and then V2 is the position that was investigated by the previous study, which is with your arm relaxed, and then you're flexing here. As you can see, the purple, you might not be able to see it, but the one that's highest is V2, so it confirmed our findings. But in interpreting this data, basically what we've realized is that our device has to be able to provide the normal torque force as well as extra to make up for patient spasticity, which is averaged by Lee et al. At 30 Newton meters. And it has to support the structure, the weight of the exoskeleton, as well as the weight of the limb itself if you're flexing, again, at this vertical position. And so we use these values to create the theoretical max torque that we would need to provide for a stroke patient. And this basically sets a baseline for us. So obviously there's a gap in this study, and many of you might find this if you would just go to the fair. Many of you might have played this game, which is called High Striker. And growing up, you might have noticed that how high you can hit is based on your age, your body size, and how well your muscles are developed. And so what we realized is that our study lacked that sense of individuality because not every patient can provide or has a spasticity of 30 Newton meters. It might be worse, it might be better, and so what we basically wanted to do is measure how much force they can provide so that then we can figure out the deficit that we need to make up for. So that led us to designing a torque force device, and here we have just preliminary designs of it. We have basically gotten to the point where we have put it together, but we're still waiting to have actual patient trials so that we can run it and from this point on, it just led us to the point where we could summarize all of our results. So what we talked about so far, our simulation confirmed all of Newton's converted Alps findings. Max torque varies depending on your arm's position. The highest torque output is when your hand is at your side, and then patients need to be tested more individually so that we can find that specific deficit, right? And then what we also realized after this is that our exo has to be able to transfer torque, but since we realized that extra weight on the arm could require more torque to be needed, we realized that maybe placing the motor at the elbow joint isn't the best choice. So what we found is maybe placing it at the shoulder would work best because it's at the center of gravity, it's closer to the center of gravity of the patient. It would place less stress on their arm, and then you can still transfer torque just as efficiently with the pulley system. In future studies, we hope to build off of our simulation and again use our torque force device to actually find those values for certain stroke patients, and then we want to see how efficient our devices are at transferring this torque by testing it with actual patients. So if we take it back to Wally, essentially in doing this, we want to invoke the same sort of hope in stroke patients as our friend Wally did in his own film, right? Because we want to make them feel like eventually they'll get to the point where they can be satisfied with their bodies, right? And so in exploring the potential that these devices have, we hope to get to that point. At this point, I'd like to acknowledge the NCSSM Foundation, Dr. Xiaozhang Hu, my mentor, my two grad students, Luis Vargas and Henry Shin, as well as the entirety of the mentorship team, which includes instructors, my peers, the drivers at the Carolina Livery, for getting us to our location safely, and for making this entire experience possible. We're excited. Are there any questions? Okay, so my primary role in this project was creating the models. And so in doing that, I had to do a lot of CADing, which came pretty easily to me, but the difficult part was having to go back to my mentor and presenting it to them, my entire team, and basically they were like, well, let's try this instead, right? And it would be multiple iterations of that just over and over again until we finally got to something that we were like relatively okay with. Like we're still creating new models even now to just test a bunch of different models. And I think to me, like once I finally got a model that they enjoyed, I felt really good with it. But up to that process, it was killer, basically, yeah. Yes?
What kind of range of disability did you limit your study to? Like with stroke, there's a huge range between like muscle weakness and complete paralysis. And what did you guys look at primarily?
So our lab works with a variety of stroke patients because what we also do is we do like nerve stimulation. And so I think it wasn't necessarily just like the range of like spasticity, for example. It was more like how well can they use their upper body, right? Because if they had something that we could work with, that made it easier for us to like find that deficit. But then at the same time, we just wanted to make sure that they were comfortable with it, because otherwise, like again, we're not to the stage where we're actually putting it on patients, but we want them to feel as comfortable as possible. Yes.
I don't know if you're like there yet, but what is the thing that triggers the arm to like either flex or extend, like based off of the patient's commands, or is this more like a physical therapy thing?
It's not necessarily physical therapy, but because of like the internal bleeding or the basically restriction of blood flow, any part of the brain can be damaged, and it's really that damage that causes the permanent contractions. That's what you were asking about?
No, I was asking like for the exoskeleton, like when is it known to flex or contract or to like assist the patient? When does it start to move?
Okay, so that's where the force sensors come in, and basically it would be able to, I guess I'm gonna say feel the amount of force that the patient is putting on like a front plate versus the back plate, and that would assist in like if it's on the front, the device would basically be programmed to help depending on whether or not the patient is struggling with that, right? So if it was different on the other end, if they were starting to push back, that's when it would help. And then it would just have to be programmed specifically